All right, well, let's see now. So that would be 0 to 1 root 1 plus the derivative, which of course bring down the power, reduce the power by 1, bring down the power, reduce the power by 1 squared. So that's 0, 1 root 1 plus 1 over 4y. So I think we saw something like this earlier. We want to try and get the 4y here. Was that it? And then it's 4y plus 1. Is that right? Something like that, was it? And then oh no, that's not it. There's something else to it. I don't quite think it's that. Because there's no square here on the y, so I can't really see how that's helpful. Would a substitution help? It might actually. If I say u equals 4y plus 1, the top would be u. No, that would make it worse. What to do here now? What's to do here? Return the power, reduce the power by 1. Could we leave it as that? A quarter y minus 1. Reduce the power by 1. I think we need to get a square in somehow. Oh, this is actually kind of tough, even though it doesn't look tough. Just 4y plus 1 over 4y. Root the whole thing. Bum, 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 bum. If I use the substitution here, that won't help too much. I'm gonna have to think about this now. Oh, I was noticing here it says use technology for the following exercise. Find the length of the functions y for a given interval. If you cannot evaluate the integral exactly, use technology to approximate it. The problem is I can get this exact, but the means seem to be a little bit beyond what is in the book. And I just think there's an interesting symmetry here between the two in a way, kind of, where this is a t and this is not. So yeah, I'm not sure if I should try without the calculator. Okay, so I'm thinking I might just use a sort of numerical approach, but I'm going to at least try substitution, see how far that gets me. U equals 4y plus 1. So du, I'm not too happy about this, but du dy equals 4. So this will be 0 to 1. Root, and on the top would be u, and on the bottom is u minus 1. And then a quarter du. So I don't really consider that an improvement much. I feel like I need some kind of square. Like I need to say let u equals v squared, maybe. So then that means du dv equals 2v. Could that work? So that would be 0 to 1. And then on the top be root u, which is root v squared, which is v. And then on the bottom it'd be root u, which is v squared minus 1. And then the quarter's still there. And the du is 2v dv. So that cancels with that to make it 2. So that's a half 0 to 1 v squared over root v squared minus 1 dv. Not v. Yes, v squared. Is that better or is that worse? Down the power, reduce the power by 1, multiplied by the inside derivative. Would another substitution make progress here? Difference of 2 squares. Be great if I could get rid of this root somehow. Better or is that any worse? The limits, of course, I'll need to change. Any better or any worse? I was to use w equals root v squared minus 1, then dw dv would be a half 1 over root v squared minus 1 2v, so the 2's would cancel. So dv would be root v squared minus 1 over v. Is that better or is that worse? dw. Because then this becomes a half 0 1 v squared over w, and then root v squared, which actually I suppose is w, over v, dw. So the w's strangely cancel out, and then the v cancels with the v. So I'll just need to replace the v from here, which would be w squared plus 1 with a root dw. Now, that is an integration, but strangely it's a trig one, and I thought the answer was going to have a log in it, so I think I might have gone possibly astray here. Let's see what I can do now with another substitution. Well, where does this one go? We say w, it's draw a little triangle, isn't it? And then that's w1, and then that's root w squared plus 1, and then that's theta. So this one is it's like it's a 1 over tan or something, is it? That 0 to 1, or whatever the limits are, 1 over cos theta. But we could say tan theta equals W. So dw d theta, the derivative of tan, which is 1 over cos squared theta. So that means dw is d theta over cos squared theta. So this root is 1 over cos, and then the dw is d theta over cos squared theta. Oh dear. Hang on. I think I've done something wrong. Let me pause for a moment. Right, so the problem is, at this point, in fact, the substitution we need is not really what I think we've done yet. It's a hyperbolic substitution, where you say, I think W equals hyperbolic sine, I don't know, theta or something. So then the integration becomes a half 0 to 1 root hyperbolic sine squared theta plus 1, which is then cos. And then the W d theta, that's hyperbolic cos. So the dw can get replaced by cos there. So then that's a half 0, 1. That's a cos and that's a cos. So now that becomes hyperbolic cos squared. All right, hang on. We'll get there. The problem is now I need some hyperbolic identities. Let's see. Not that one. Huh? Come on. Let's see now. Calculus. Let's see. I need some hyperbolic identities. The definition of the inverse functions. Here we go. I need a double angle one. Maybe this one here. And let's see. Yeah, I could say I make x equal to y. I have hyper cos 2 theta equals cos squared plus sine squared. And then I can do a switcheroo here on the sine, because I can say the sine is cos squared minus 1. So cos 2 theta plus 1, that's 2 of them. Divide by 2. So 1 plus cos 2 theta. Okay. A half 1 plus cos 2 theta over 2 d theta. So that's a half theta plus a quarter sine 2 theta. Now the only problem is those 0 and 1, they were for y, and I've completely lost track of my substitutions at this point. Let me just copy this side here. Okay, and let's just go back in time to get the substitutions back up. Okay, let me just look out some paper and a pen and write these down. So the first one was u equals 4y plus 1, and then u equals v squared, and then w equals root v squared minus 1, and then put now then I can put this one here, and then it was w equals hypersine, and the y was 0 to 1. And now actually I need, I don't need the inverse function because it's just going to be, all right, it's just going to be, now let's see, theta over 4 plus 1 over 8, and then that's over 2, e 2 theta minus e minus 2 theta. Okay, now let's try and figure out the substitution. So y went from 0 to 1, and the first substitution was u equals 4y plus 1. So when y is 0, the u is going from 1, and then when the y is 1, then the u goes up to 5. Then the next one is u equals v squared. So when the u is 1, the v is 1, but when the u is 5, the v is actually root 5. And I realize there's a plus or minus issue here, which I'm just going to hope it's not going to mess things up and just pretend I don't see that. And then the w, but this doesn't get the log, this gets e. So I think there was supposed to be an inverse function here somewhere. I think, oh, maybe. Oh, this is where it comes in. I need it here. Hypersine theta. For the w. Oh, wait, hang on. I missed my w. W is root v squared minus 1. So when the v is 1, then the w is 0. And when the v is root 5, that's 5 minus 1 is 4. So that's 2. Then we have finally theta then would actually be the sine inverse function of w. So theta would go to sine inverse, hypersine inverse 0 to hypersine inverse w, which is 2 then. So now I need the hypersine inverse function definitions, which I saw somewhere a moment ago. That's log, so that's log root x, or in this case, w plus, not root there, come on. Log w plus root w squared plus 1. Okay. Okay. So then that would mean put in 0. That's 0, 0, root 1, log root 1. That's 0. 2. And then if we put in 2, 2 squared is 4. 4 plus 1 is 5. So that's log 2 plus root 5. So let's put that in first. So that would be log 2 plus root 5 over 4 plus over 16 e power. So you could take the 2 out, and just say it's e theta squared. And take the minus 2 out, minus 2 there. Okay, so e and log cancel, so it's just 2 plus root 5 squared minus, and then 1 over 2 plus root 5 squared over 16. And then minus, putting in 0. E power 0 is 1. E power 0. Okay, so that's gone, thankfully. So now if I type this in on my calculator, I'd be quite amazed if I got the right answer after all of that. Let's see, 2 plus root 5 squared minus 1 over 2 plus root 5 squared, and and then let's see, that is 1.48 roughly. Now, is there any possibility that that's actually the correct answer? Let's see, 0 to 1 root 1 plus that squared, 1, the derivative, bring down the power, and then reduce the power by 1. Bring down the squared. What's wrong with this? From 0 to 1, 1 plus the derivative squared, and the derivative is bring down the power and then reduce the power by 1. Where's the same maths error? Oh, because of the 0. Because of the 0? Doesn't like starting at 0, huh? Maybe fudge it a bit. Doesn't like the 0. Let's see, I think so I've used my simple little Casio calculator to calculate this, and it's not exact because Casio doesn't like the limit starting at 0, but it's actually remarkably close, 1.45. So maybe if I was to use some actual math software instead of just a simple Casio, let's see, what is it now? Square root 1 plus a half, and then y power minus a half. And then that needs to be squared. Get that right. 1 plus, yeah, and let's just integrate this from 0 to 1. 1.47, so 1.48. And I'm absolutely flabbergasted that I got this right. Absolutely unbelievable. And it only took 24 minutes.